This is a recast of the 5,400-word piece, Artificial Neural Networks, ANNs, from Synaptic AI. This article covers the structure, components, and applications of artificial neural networks. Let's listen in.
Artificial neural networks, or ANNs, are machine learning models based on the structure and function of the human brain. They are used for things like pattern recognition, image and voice recognition, natural language processing, and predictive analytics.
Artificial neural networks have a rich history in the field of cybernetics and were developed in the 1940s by Warren McCulloch and Walter Pitts, and later by Frank Rosenblatt.
They've evolved over time to become more complex and powerful, and now play a major role in current technology due to their ability to solve complex problems that traditional programming methods may struggle with.
So let's talk about the components of an ANN. What makes them so powerful?
ANNs are made up of nodes, also known as artificial neurons, that are interconnected through various layers. Each node receives inputs, processes the information, and sends it to a connected node until final output is produced. The nodes also have weights that determine the strength of the connections between them.
That's right. The weights can be adjusted during the learning process so that the network can accurately classify or predict new data. It's important that the weights are properly tuned for effective learning in ANNs.
And these networks have many applications in industries ranging from finance to healthcare to gaming.
The first is activation functions, which is used to introduce nonlinearity into the output of a neuron. A neuron is activated when a certain threshold value is exceeded, and the most common activation functions are sigmoid, ReLU, and tan.
Sigmoid functions output values between 0 and 1, so they are useful in binary classifications. ReLU is a more computationally efficient function, and it can help avoid the vanishing gradient problem. Tan is similar to sigmoid, but outputs values between -1 and 1.
Another concept we should discuss is layers. These are essential components in the design and functioning of ANNs. Multiple layers enable them to learn complex patterns and generalize from large data sets.
In feed-forward networks, information moves from the input through hidden layers to the output layer, whereas convolutional neural networks introduce convolutional layers to learn spatial relations of image features. Recurrent neural networks use loops to process sequences of data, such as text and speech.
Finally, there are inputs and outputs, which are critical components of ANNs. Inputs are the data fed into the network, while outputs are the results or predictions generated by it. ANNs are designed to learn from examples, and accuracy of outputs improves over time as the network processes more data and learns from its mistakes.
As you can see, ANNs have tremendous potential in various fields and continue to evolve as researchers work on improving accuracy and efficiency while ensuring ethical use.
One of the most common applications of ANNs is image and speech recognition. Image recognition involves detecting and classifying objects within an image, while speech recognition is the transcription and interpretation of spoken language into text or commands.
You might have already experienced this yourself with voice-activated assistants, transcription software, and phone systems.
Another example is natural language processing, which involves tasks such as language translation, chatbots, and voice recognition. It enables machines to understand the human language and is used in industries such as healthcare, finance, and customer service.
Finally, ANNs are also powerful tools for time series prediction. Time series data captures trends and patterns over a specific time interval, which can be analyzed to forecast future values. ANNs are capable of modeling complex time series data and identifying hidden patterns.
Thus, ANNs have the potential to revolutionize time series prediction and forecasting, leading to more informed decision-making and greater efficiency.
That's right. Also, ANNs can be used in various industries. In healthcare, they can be used to diagnose illnesses and predict patient outcomes. In finance, they can be used for fraud detection and to measure stock market trends.
In the automotive industry, they can be used to optimize fuel consumption and improve road safety. They can also be used in speech and image recognition, natural language processing, and robotics. So as you can see, the applications of ANNs are widespread across various industries.
Absolutely. There are a few advantages of using ANNs as well. One major benefit is their capacity to process information in a parallel manner. ANNs can process several information inputs simultaneously, making them suitable for complex and time-sensitive applications.
Furthermore, ANNs can learn by example and generalize from the data. This feature enables them to make accurate predictions when presented with new data. ANNs are also robust to noisy data and can handle incomplete data sets, making them useful in many real-world applications.
Additionally, ANNs are highly flexible and adaptable, making them suitable for a wide range of applications. They can learn from their own mistakes and adapt to new data, reducing the need for human intervention and improving their overall efficiency. These features make ANNs a valuable tool for a wide range of applications.
Right. Another key advantage of artificial neural networks is their ability to perform fast and efficient computations. The parallel processing capabilities of ANNs enable them to handle massive amounts of data simultaneously, allowing for quick data analysis and decision-making.
That's a great point. All right, so it looks like we've covered the key points from the article.
Yep.
Right. It mentions that ANNs struggle to explain their decisions and require large datasets for training.
In addition, computational complexity can lead to slower training times and bias can occur from lack of diversity in training data.
Absolutely. The article also points out that ANNs are prone to attacks, like adversarial attacks, and that there's a need for techniques to increase their robustness.
Right? Researchers have been working on ways to make networks more resistant to these attacks.
Exactly. ANNs have found applications in lots of areas, like facial recognition, medical diagnosis, and even finance.
And it looks like the future of ANNs is very promising. With more sophisticated deep learning algorithms, enhanced computing power, and more data available, their potential is almost limitless.
Indeed.
The potential impact of ANNs on various industries is also huge. They can streamline operations, reduce costs, and improve overall efficiency. For example, in healthcare they can be used for disease diagnosis, drug discovery, and personalized treatments.
Of course, when using ANNs, there are ethical considerations. We must ensure that inputs and distributions used in training the network are unbiased, and that the data is in compliance with all privacy policies.
Absolutely.
For those not familiar with ANNs, they are computational models inspired by the human brain. They consist of multiple layers of interconnected nodes which can process and learn from input data.
And learning in ANNs is achieved through techniques like backpropagation, which adjusts the weights of the connections between nodes to minimize the error between predicted outputs and actuals.
Despite their success, ANNs still face challenges in performance scaling and interpretability.
Despite these challenges, it is clear that ANNs are increasingly becoming a vital tool in current and future technology. This makes it essential that research and development efforts focus on enhancing accuracy, efficiency, performance, and scalability of ANNs while exploring new use cases and applications.